the exam.
There you go.
Solutions are posted. I didn't take off a lot of points for small things. So like if an integral was set up correctly and kind of the first stage things was done correctly, but for some reason the number is just off a little bit for just evaluating kind of the final step. But the basic idea, the fundamental, the more important idea of how to go about setting up, how to set up the problem and how to get going on it was set up. I gave just about all the points. So there are a few details in there. So even if you've got like a 1 point off, you might just check some of the details of the solution. It would be good even if you got all the points, when it comes time to studying, to review, because there might be a few more details included with the solutions. For some of the problems, it says, what is the distribution after you transform this? Well, a lot of people gave me the mean and standard deviation, and maybe said it was normal, but maybe not as much explanation. You could use moment generating functions to show that. Generally, I allowed that to be counted for points because it was in the right, the vein of giving me useful information about it. For any problem like that, sometimes you can give a few more details. So the solutions are posted there with a few more details, but generally I think the class did a really great job in that material. Right? So over the next couple of days, Tuesday and Thursday, we're going to talk about material chapter 7. I'll post homework soon that would be due next week that covers these methods of transformations. Right? Right, and then we'll do more things after that with limits and things like that. Yes?
Do you have another homework due on Thursday?
There's not one due this Thursday, so it's been moved off. I'd like a couple of days to talk about these transformations. Right? So things are a little bit spread out. There is a Easter break. It doesn't change our class meeting time. We're on Tuesday, Thursday, but Monday, Friday are a break, and then so it seems like things are kind of spread out. But there is that project sitting out there to think about. This will get posted soon, hopefully today or by tomorrow morning, so that you have that to look at and work ahead on if you're managing your schedule and time and so on. But so in this, but any questions about? I've heard from a few people in this class, my other classes, about projects. So I know some of you are starting to look at ideas, thinking about websites or videos or transformations or games of chance or something that you can write about. And so often people have a couple ideas. I'd like to do something on this, and if you send me some ideas or we meet during office hours or sometime, a little discussion can kind of help you produce an outline, a few topics to discuss, and then it's maybe easier, I would think, to kind of fill it out and fill up the pages and organize the material so that it comes together more smoothly. So today we're going to look at material on transformations of random variables. So the idea of this is that we have a random variable that is new from the old. And so some of these things transformations are one-dimensional. Or we maybe do a linear transformation of some sort, scale it. Maybe we would instead take the square root of the original variable, and we want to know what's the random variable called after we take the square root, what's its mean, what's its variance, and things like that afterwards. Or maybe log of x in many scientific applications. Right? So given that we have one random variable and know something about its distribution, what results once we do those things? We'll have some transformations that are two-dimensional. Like y might be the average of two things, or y might be the difference of two things. If you have two random variables and either they're independent or not, and you take the difference of them, how do the means change, how do the variances change, and more importantly, how do all the probabilities change. Well, you could have other ones that are, sometimes using ratio of two random variables, right? X is X2 is maybe the number of people in the labor market, and X1 is the number of people who are employed. Well, so then that's the employment rate, or maybe the unemployment rate if you look at it that way, right? And so both of those things could be random variables. You take the ratio, what happens to the result? A lot of work in statistics goes beyond that to really n-dimensional. We take a random sample, size n, x1, x2, x3, up to xn, and then we're going to do things with that. We're going to calculate things like x bar, or maybe we're going to calculate the sample variance, or maybe we're going to report the maximum value, or maybe the 5th percentile. So we're going to do some summary of all of our data, and we want to know what's the probability distribution associated with that. Yeah.
What is the X bar notation represent?
So X bar, these are like sample mean. So if we take 1 over n times the sum of the xi's, this is arithmetic average. This is a sample variance. So it's another function, 1 over n minus 1 times the sum of all the overall the observations of the square deviations from the mean. So in statistics, that's usually used to describe the variance of a sample set of values. If we think we're going to think about it as random variables, we're going to go out and take all these measurements. If the measurements are normal, what's the distribution of the sample average? What's the distribution of the sample variance, and so on? Or what's the distribution of the 5th percentile? Can we say anything about that based on those? Right? And so those new random variables, averages, differences, other things, are useful for answering the questions we want to answer about things. Right? What is the variability? What are the averages? What are extremes? Right? And so on. And so this section is about how do you get ideas of what those probability distributions are from the other things that we've seen so far. Right? And so a first approach, we're going to first look at discrete ones. So discrete random variables is a little bit more straightforward in the sense that you have the discrete values, the probabilities of different values of 2 or more variables, and you're taking some function of it. And sometimes you're just going to enumerate it and say what that is, right? So if we have, for instance, just so we have x is a random variable, and the values that it can take on are represented by this little x values, and we're very interested in some transformation. We're going to do something to our numbers. Right? We're going to score them somehow, weight them, change them somehow. Right? So y is a random variable. Right? Little values, we'll call those little y. And what we want to know is what's the probability that y equals one of its little values. Well, in a discrete case, some of the values of x map into this little y. That is, there are certain values of x that produce this little y. And those x's have probabilities. So we just simply add over the probability that x equals x for those cases, for those x, such that g of x equals y. So this is a little index of x values here, or maybe a set. Right? So these are the x values such that when you do the transformation on that value, you get this y value you're interested in. And if you kind of clump or associate those probabilities for all the different possibilities, you get the probability. Right? So it's kind of an adding, accounting approach to adding these probabilities. Right? So discrete conceptually then it's not so different. So, but we can take an example, just as an example, say we roll 2 pair dice, pair 6-sided dice. So we get the numbers 1 through 6 for the first one, say, and 1 through 6 for the second one. So there's all of these 36 possibilities that we can have. So 36 pairs are possible. So they're fair and independent and so on. The probability of any particular pair is going to be just 1 out of 36. And so the type of functions or summaries we might do something like, well, let's look at the minimum and maximum, right? We could look at something like the maximum value, right? The maximum values can take on values 6, 3, 2, or 1. And this kind of abstract notation means that for every possible maximum value, like 6, is what combinations of the other pairs give you that outcome. So for a maximum of 6, the maximum of 6 occurs at all these places. Right? You get a 6 on the first one or a 6 on the second one, right? You get this maximum of 6. That occurs 11 times. The maximum of 5, right, occurs in this next set here. There's 1, 2, 3, 4, 5, 6, 7, 8, 9 times that you can get a maximum of 6. I mean 5, sorry. And then 4, well, you have to get at least 4 on one of them, but not more than 4 on either one, so that's 7 of those times happen. And it goes down. To get a maximum of 1, you just have to just 1 time. Right? So that's taking this random variable that are these pairs, or 2 random variables, 2 values, right? And taking some summary, some transformation of it, and getting that, yeah.
You're saying a maximum of like 6.
Yeah.
For example, are you saying you need to have at least 1 6?
Yeah. Yeah. So the maximum on these 2 dice rolls, right? So that you get the largest of the 2. So you need to get at least 1 6. The maximum of 5 is not really saying that you get at least 1 5. I mean, it's at least 1 5 and no 6s. So this one is a maximum between 5 and 1, the maximum is 5. Between 5 and 2, the maximum is 5, and so on. So these 5s kind of go along here. So the pattern of the maximum outcomes, right, the maximum of, you get 2 1, 2 2, or 1 2, the maximum is 2, and so it's kind of counting that. But you could do that with any number of other things. You could look at the minimum. You could look at the absolute difference between a couple values. Right? In this case, you only get different values. The biggest difference between the first and second die can be 5 at most, and they can be the same. So it's a different outcome. But if you wanted to find those probabilities, you would just take all the different outcomes and map them in. And so that's one way for discrete to get that transformation. This is kind of a brute force, right? Counting, accumulating type of thing, but that's a transformation. A second way that we've done with we did some things using moment generating functions. So for instance, if x1 is binomial random variable in one trials and some probability of XSP, the moment generating function of m1 of this one, there was a p e to the t plus 1 minus p raised to the n1 power. And if we had a second binomial, independent of that, and if it was another binomial, another set of trials in two trials, if it had the same probability p, its moment generating function would look, basically the same, except for n2 up here. And if our new random variable is x1 plus x2, right, the total number, the moment generating function of the sum when they're independent is just the product of those two things. We talked about that and used that fact. It's going to be the product of the two moment generating functions. And so it's, right, you're just adding the exponents up here. And this thing is a moment generating function of a binomial with n1 plus n2 trials and a probability of p. And it has the support that you expect 0 to n1 plus n2 is a possible count. And that moment generating function, if there's a uniqueness, it says that it is that distribution. So sometimes moment generating functions gave us some things that we could use for these. Right? Yeah.
Does that work as cleanly if the binomials have different probabilities?
They have different probabilities, no, right? Because you're going to have P1 here and P2 here if they're different. And so it's kind of a limited application. The moment generating functions have to match up just right for it to work out. Right? But they can be different sample sizes as long as they're added together with this case. So we already know how the first one with kind of just accounting and counting things up seems kind of straightforward and not that innovative and new. We've used moment generating functions, so we've done this. And so this could also work for things like geometrics or negative binomials. There are a few other cases, or Poissons. Right? If you add Poissons together, it adds the rates. So there's a few other binomial, things like discrete ones. There's the third way we can do these things is kind of a convolution method. And again, this really applies, well, it works for sums, but there would be versions of this that would work for other things. Right? So again, if that case with the binomial case, so if y equals x1 plus x2, and let's say that both these are the same. They don't necessarily have to be the same, but it's a little bit easier to show something here. The same random variables. You do it once, and you do it again, and you're going to add them all together. What's the probability that y equals one of its values? Well, if you do the moment generating thing, you can say, well, we know what binomial it is, so I can just write down the probability, the binomial probability. But this convolution idea, what you really have is a probability that x1 equals a certain value and x2 equals a certain value. When you have these two random variables. And for certain pairs of x1 and x2, if x2 plus x1 plus x2 equals y, and we add up those probabilities such that it equals the sum we want, that would be the probability. Y can go from 0 to n. It's an integer. Right? 2n, sorry. Each of these goes from 0 to n, and this one goes from 0 to n. You add them up. look at these integers, there are certain values of x1 and x2 that add up to those numbers. And if you find all the places that they have those probabilities, that's how it works out. And so if, let's say y is less than or equal to n to begin with, right? Well, we could say x1 is some value here. Let's just call it k as its value. If they're independent, we can write it as the product of two things here. Now, if x1 equals k, some value, what's the value of y2? I mean, x2. So x1 plus x2 have to equal 1. If we call this one k, then x2 has to be y minus k. So it's y minus k. Over here, they're independent. If they're independent random variables, then their probabilities multiply. And what values of k are possible? So if y is less than n, then we can go all the way up to y. So maybe x1 takes up the whole thing, and then x2 is 0. Or x1 takes up part of it, and then y2 makes up the rest. Each of these things are binomial probabilities. So there's n choose k, p to the k, 1 minus p, n minus k. And this is also binomial probability. And I made them all the same. P to the y minus k, 1 minus p. Now there's n cases, so y minus k is over here. That's just writing down the two binomial probabilities. Yes.
Why did the range of y change from less than equal to 2n to just n?
So y, so it can go anywhere in here, right? We could, let's just first consider, right, the case where it's less than halfway. The virtue of that is that x could make up the whole thing, and then x2 could make up the rest. If y was greater than n, then you can't have 0 for the first one. Because if it's more than halfway, well, you have to have something in the first one, otherwise it doesn't quite work. It doesn't add, it can't add up to more than n. Just the maximum for the second one is n. So if this is bigger, so it would just change these limits on there to make it kind of work out. So what do we get here? Right? Well, there's an n choose k, and there's an n choose y minus k. But is k involved with those proportions? Right? There's a p to the k, p to the y minus k. So there's a p to the y. You can add those together. And there's a 1 minus p. If you add these two things together, of just n minus y. And we did things with identities, or combinatorial things, right? Binomial theorem at the beginning, early in the course. This is one example where this thing was one of those special ones, that this is a n choose y. You're going to choose, you have n objects, or 2n choose y. And this must be 2n, sorry. There's an n in both of those cases, so 2n minus y. So what we get in the end is 2n choose y, p to the y, 1 minus p to the And that looks like, that is, a binomial probability. Working through this. If you take a y being greater than n, you get different limits, but still the same thing works out.
Where did the Q go in the exponent?
Sorry, it's still there. You usually don't put it as 2n, you put it inside. But anyway, this is a convolution. This is a binomial probability. And if you consider the other case, you get it works out as well, binomial probability. So, for some of these things for discrete, you just add them up and figure out how to combine. Sometimes that adding up process of finding all the cases where, you know, it can be written down kind of in a formula, and generally this type of thing is called convolution for these two. There's kind of a continuous version of it that we'll do later for continuous ones. Right? And for some cases, it's the moment generating function. Right? So you can get new random variables and figure out what they are, and that would give you the probabilities, the means, the variances, and other things that you need. Right? So discrete transformations is one thing that happens. Right? Mostly we're going to focus on, we have a problem on that, but looking at the continuous one. Right? What happens with continuous random variables when they transform? So, but any questions on the discrete side of things? So it's kind of some examples of how you get new random variables from both lines. Focusing more on continuous ones. One method that we're going to look at today uses the CDF, or cumulative. So let's say if x is a random variable, then the CDF of x is probability that the random variable is less than or equal to a certain value. The density, relate to that by taking a derivative. Right? Density of x, PDF, the probability density function, f of x, is the derivative of that. Dx of that function. So either the cumulative or the density or kind of the name of the random variable, if it's a special type, tells you what it is. Now we're going to do one of those transformations to this one variable. Square root, absolute value, something or other. Right? So y is some g of x. And so this CDF method asks the question, what is y? What's the cumulative distribution function for our y variable? And if that's something that we can use, we have that function. We can put it in percentiles, f to percentiles. If we differentiate that f of y function, we can get the density. We can get means, variances, and other things that would be useful for us. Right? So is there a way we can? Yeah. Let's start with the definition. What's the definition of f? Fy of y is the probability that y is less than or equal to some value. Right, that's what we want. So let's substitute our transformation. Y equals g of x, so let's put g of x in there. Now, if we can invert this function, right, if we can invert this is a one-to-one function and we can invert it, then we can take the inverse of this. G inverse is the inverse of that function. So if you're squaring something, squaring positive values, then square root is the inverse. Right? Multiplying it by 10, then dividing by 10 is the inverse. And so exponentiating something or then taking logs, it takes it back and forth between those. But what is this? The probability that x is less than some value, right? There's y value with that transformation applied. That's the CDF of x. So this is the CDF of x evaluated at this inverse value. So we're going to go through that process of change in some examples. And then we're going to differentiate this to get back to the density. But we'll show that in the second step, right? So let's look at one example of how this works. So let's say x is an exponential random variable. So the density of x is one of these decreasing functions. We have of x density functions. The f of x is 1 over theta, e to the negative x over theta. X are positive random variables. The cumulative distribution function of x is the integral from 0 up to x of, I'm going to put a little placeholder in there, of that thing, of the density from 0 up to x, is 1 minus e to the negative x over theta is what it comes out to be. Let's say we scale. So this is kind of a waiting time. Maybe it's a waiting time in seconds or minutes or something like that. Now we're going to change to hours or milliseconds. You know, one way or the other, we're changing it. So y is some gamma times x, or gamma is some number greater than 0. What's the distribution of y? We could do part of this thing by just looking at means and variances, right? But what's the whole distribution? The CDF method, right? Cumulative distribution of y, the probability that y is less than or equal to a value. So it's the probability that gamma x is less than or equal to that value. So it's the probability that x is less than or equal to y over gamma, a scaled value. So it's 1 minus, because of that, the e to the negative. Now y over gamma goes into that spot for x over theta. And if we rewrite that a little bit, we get the e to the negative y over gamma. So that's the CDF. We could make note, I guess, that really the CDF for this one is when x is greater than 0. When x is greater than 0, y is also greater than 0. So this one really works here for y greater than 0. Fine. And so what does that look like? Right. That looks like another exponential, the CDF of an exponential. It matches the form. What's the density? I would be differentiating this thing with respect to y, and you're going to end up with, you do that and use the chain rule. You end up with that thing. So because of this, we know that y, which was x times this thing, is an exponential random variable, and the new parameter in there is that gamma times the original one. So you can scale an exponential with a positive scale, and it's still exponential. So the means and variances are still exponential formulas for those. And yep, probability cumulatives would be calculated according to the exponential formula, and that shows that it's that distribution, that it's that probability. So that's, besides, we've kind of looked at mode generating functions before, but this CDF, right, is a general method, right? You can do it with other transformations. But any questions on this one? So let's look at another example, right? So let's say that X is uniform between 0 and 1. So the density of X is just 1 on the unit interval there. The cumulative distribution of X is the probability that X is less than or equal to some value. And on that interval, it's just X. It just accumulates area under the density curve at a constant rate, so the further you go out, the more and more it grows. Let's say y equals x squared. We're going to square the random variable. So maybe this is like an area. It's like a radius of some sort. Randomly picking trees, if the distribution of trees is uniform in terms of radius, right, then what's the distribution in terms of the area? How do we go? We need to, we want the density, the cumulative for y, so the probability y is equal to y. Put x squared in there. Right? And then we do the inverse transformation, right? Because it's between 0 and 1, the inverse of the square is just the square root. X is less than or equal to the square root of y. So what's the cumulative? This is the probability X is less than or equal to that. Right? It's just whatever it was. Right? It's just because of the uniform. It's just square root of y. So what's the density of y? We take the derivative of that thing. We get the probability density function. F prime of y. So the derivative of that is 1/2, and then there's y to the negative 1/2, so it's 1 over the square root of y. And if x was between 0 and 1, y is between 0 and 1 for the square. So that's the probability density function of y. And so you can do things like that. What is the expectation of y? And you could do the integral from 0 to 1 of y times this new density that we found. So that's y to the 1/2, so there's a y to the 3/2. this is the 3/2, so down at the bottom. You evaluate that at y equals 0 to 1. So it ends up being 1/3. So we got this, this thing that's like area, the new average, right? The average of x was 1/2, right? Because it was uniform between 0 and 1, right? Squaring it, squaring things below 1 makes the numbers go smaller, right? And so the average is less. That would figure that one out. What about, sometimes you have to adapt just a little bit. Say x is uniform between -2 and 2. Well, let's do something a little bit different, right? Between -pi and pi. So this kind of angle, right? We're thinking about, minus 180 degrees or positive 180 degrees, kind of going in that kind of circle. So the density of x, right, is 1 over 2 pi, because it's uniform between the distance between the endpoints is 2 pi. The cumulative distribution of x for something in this range is our distance to the bottom one. So it's minus, you put a negative pi over here. And then the distance is 2 pi over there. So it would be x plus pi right over 2 pi in that interval. So if x is at the lower point, if it's at negative pi, then it's just 0. There's no probability yet. And as you go at 0, it's 1/2, and at pi, it's going to be 1. So it's going to accumulate all during there. Well, let's say we're not interested in the exact angle we're going at, but just the deviation from 0. How far off is it? So y is the absolute value of x. So sometimes if things aren't 1-to-1, you can still figure things out, right? But you got to look at how you would look at the cumulative distribution of y. Probably y is less than or equal to y. Writing the same thing then again. This one, the inverse is not 1-to-1, but we can describe the space where it's less than some number, right? So if this is less than 0 to pi, right, just logically, if x is in this range, then the absolute value has to be in that range. So if the absolute value of x is less than 1, we can write that without the absolute value. So negative y is less than or equal to x is less than or equal to y. It has to be close enough to 0 so that the absolute distance is not bigger. This has 2 parts, right? Just because of the absolute value, not a 1-to-1 function. So this could be the cumulative distribution of x at y minus the cumulative distribution of x at negative y. That was the probability between 2 points. You make the probability less than the upper end point and subtract out below the lower end point. Right? And so if you put those things in there, y plus pi over 2 pi minus negative y plus pi over 2 pi. Terms in there, so the minus minus makes it 2y over 2 pi, or just y over pi as the cumulative. So if you have a cumulative distribution function like this one, right, that between, graph it 0 to pi, that's the only values of y we're talking about here. And at a maximum, right, this one, it just kind of goes up here to 1, and it's going to be 0 before and after, because x, well, I guess it's not 5 before, right? Can't be negative, right? This kind of constant increase is also uniform. Right? The y turns out to be a uniform random variable on 0 to pi. Right? So it's can you take something that's uniform on 0 to 2 pi, essentially fold it over, and it still is uniform, but now on only half the space, right? If you differentiate this thing, so this is f1, the capital one. Right? If you differentiate that, just get 1/5 constant. So it's uniform. So you know then it's uniform density. And once you know that, you know the mean, you can figure out the mean, the variance from the standard formulas. It's easy to find different probabilities related to that. And that's the new random variable. Any questions about? So, let me write this out. Density of the noise constant. So we've kind of done something here a couple times where we've done the CDF and then plugged it in and solved for it, and eventually we take the derivative. So I call it, talk about it as this cumulative method when you start with the cumulatives and are focusing on the cumulative distribution function. Right? But you can kind of skip that step a little bit, right? And use PDFs directly. And so it's following through the same process really, but maybe you can think about it as saving yourself a step. Right? So let's say, x is a random variable, and x, some f of x value is cumulative distribution function, probability of x equals x. And now you're taking y as some function of x. Well, what we said before is that the cumulative distribution of y is related to the cumulative distribution of x, evaluated at g -1 of y, through what we did before. Right? So you can write the probability y is less than or equal to something, and put that g function in there, and then convert it. That's what we got. Right? But the relationship between density and the PDF and the cumulative one is a derivative. Right? So if we want the density of y, that's a derivative of, y of that one. Well, that's a derivative of this thing. So you're going to get a chain rule thing going on, right? You take a derivative of this one. And then you have to take a derivative of this one. And it works out that you end up taking the absolute value of that thing. It might be negative when you take the derivative, but you have to take the densities are positive. And the calculus works out if you go through it carefully. That is positive. So I talk about this as call this more the PDF method. You start with the PDF method of x. So this is showing that a little bit better. This is the PDF of x evaluated at the inverse point, and then the derivative. So you can get the PDF of y, the density function, by taking the density function of x at that inverse, and then multiplying that extra piece there. In calculus, this is like the dx. This is like the scale change, right? Dx going from the dx measure to the dy measure. So that scale change is incorporated there. We'll look at it in an example. Okay?
Absolute values in parentheses.
These are absolute values. Right? It ends up it would be an absolute value one way or the other. Right? Let's start with, as an example of this. Let's say that x is a normal random variable with mean 0 and variance. So the density of x is our bell-shaped curve, right, centered at 0, right, with a standard deviation of 1. Let's say we take y to the ex. Y is actually a distribution, it's called log normal. Right? It's very skewed, right? Very non-symmetric. High volatility, financial things, extreme energy things in astrophysics get modeled with this log normal distribution. Right? What is the density of Y? If you took the log of this, it would be back to normal, so that's why it's called log normal. It's not normal itself. What is the density? Well, to do this, so this is our g of x function. So y equals, you have to invert that. So we need to solve for x, and so that's the natural log of y. And then we're going to need to take a derivative of that. So we're going to take the dx dy is just 1 over 1. E to any power is positive. Right, so this y is greater than 0, whatever x is. Right? If x goes to negative infinity, e to that something that's very, very small is going to 0. So what's f of this? Right? The formula says your density of x evaluated at the transformation. Right? So this thing goes in here. But we've done a scale change. We're not doing linear change. We're changing space by taking the logs of everything. Right? So this extra piece goes over here. And if we write that out, right, so there's 1 over square root of 2 pi e to the negative x squared. So it's a natural log of y squared over 2. And then there's an extra 1 over y, for y greater than 0. That, for what it's worth, is the density function. Right, probability density function. That's how you would go about it, right? It's not as easy to use. You can, there's mean, variance, moment generating functions for these things, right? But that would be the process of figuring out, well, what is the density? And there's the density. What if we reverse the process? What if we start out with this one and go backwards? Or we should get back to normal, right? So let's say that y is this thing called a log normal. That parameter is 0 and 1. So there's log normal with mu and sigmas too, as more general cases. So this would be, what was it, 1 over square root of 2 pi. And there's e is the negative natural log of y. That's squared over 2. And there's a 1 over y for negative 0. It's less than y. So that's log normal, highly skewed. But let's say we want to get back to normal because we have normal tables and we can look up normal probabilities and things like that. So let's let x equal the natural log of y. All right, that should get us back to normal. Let's show that it's that density, that it's actually normal density. So the question is, what is fx? We got to do the inverse, right? So y is the inverse of this thing, solving for y is dx, dy dx. It's just d to the x. It doesn't change, right? And it's positive, so there's no positive value doesn't really enter into it. So this fx of x, so now we're kind of doing it backwards. It's the y1, the one we started with, and inverse transformation, right? So that inverse thing goes into there. And then we gotta get this extra thing out here. And so we're plugging e to the x into this place where we have y there. So 1 over 2 pi square root e to the negative, there's a natural log of e to the x over 2. And there's 1 over e to the x here, and we multiply by another e to the x there. E to the x, no, e to the square, right? This thing is supposed to be natural log of 2 pi, that's supposed to be squared. I have a square. All right, so where there was a y in this function, I've plugged in ex. Those two spots. And now these two cancel, so that's gone, right? And the natural log of e to a power is just that x thing, right? So this is just 1 over 2 pi square root e to the x squared over 2, and that's it. And if y is in 0 to 1, right, then the natural log of y, which is our x value, that maps to the whole real line. The natural log of something near 0 goes negative like that. This is 0 to infinity. Right? So y was on the positive real line. Taking the log of it stretches it out. So there's something to keeping track of, the actual support of these things, what numbers are also actually possible. So that's in the negative A. Right? So this thing is a standard normal density, normal 0, 1 density. So we went to the logs, we exponentiated to make it log normal, right? And then undoing it, taking the log, brings it back to normal, and it worked out. So instead of exactly dealing with the CDF, sometimes you can just deal with the densities. Yeah.
A little higher on the slide, it said, oh, never mind. I just got it wrong in my head.
Any other? So sometimes it's easier to deal with them. CDFs, and eventually you differentiate, but sometimes you can go directly there. So if things are not one-to-one, one last example for today. Right? Let's say x is normal 0, 1, random variable, and y equals x squared. What is the density of y now? Well, this is not a one-to-one function. That for the values of x, this goes here, and for any value of y, there are two values of x down here, right, that would produce that same value of y. So we'll have to be careful. When it's not one-to-one, it's probably easiest to write it the CDFs down. All right, so kind of like with the absolute value, we end up with this situation. X squared has to be less than something. But x can be negative or it can be positive. But that's okay. We can write it as take the square root of both sides. We're aiming to get everything. We're aiming to get in terms of x, because we know what x is. That's what we're doing. We're aiming to get things expressed in terms of the distribution of x. So at the upper end, if y is, the square root of y is up here. At the lower end, it's the negative of the square root. So there's a probability that x is less than or equal to the square root of y minus the probability that x is less than negative the square root. And so we're doing less than a value minus the other tail. So in terms of the density picture, this was our, here's 0. Here's a value y here. Here's negative 1. So if we want the area right in the middle of this, we can take the area below y and then subtract out the area below the negative. Right? Well, this is the cumulative of x at square root of y. And this is the cumulative of x at negative square root of y. So we'll take derivatives, right, to get the densities. Take the derivative of this, the density of x at the square root of y, and then you take the derivative of this, so there's a 1/2, and there's a square root of y that's down here. You take the derivative of that thing. Again, is the density of x now at the negative of square root of y. And there's a negative 1 over 2 times the square root of y that shows up there. Chain rule. And each of these x's is the normal 0, 1 density. So this one doesn't fit exactly in the, it's not 1-to-1, so it's not exactly the CDF method. It's not exactly exclusively the PDF method. You kind of have to do them both, right, to make it work out. And so what's this thing? Well, there's 1 over square root of 2 pi, and there's e to the negative x squared. That's the y squared is just simply y, so negative y over 2. And then there's a 1 over 2 square root of y. This minus becomes a plus because of that one over there. This, the density has the negative square root of y. Is exactly the same value. These should be at the same height. Right? It's symmetric about 0, it's symmetric density, so you get the same height there. So there's a square root of 2 pi, e to the negative y over 2 up here, and there's 1 over 2 square root. You put those two things together, it looks like there's a 1 over square root of 2 pi, 1 over the square root of y, and the 1/2 go away, negative y over 2. And that's the density. This happens to be something called a chi-square distribution with 1 degree of freedom. So it's a special version of a gamma random variable. You get that density, and you're like, that is actually a special form of a gamma. Therefore, I know the mean, I know the variances. I might have code that would generate random numbers or evaluate densities and things like that, or give me critical cutoff values. This is a set of y here. This is for y greater than 0. We're squaring things, everything's greater than 0. But anyway, that is kind of applying the principles and things that we've done gets you the density for that. If you had your charts and your formulas, and you saw that it was a gamma, then you would be in business, right? Because you give the means, variances, and other stuff that you want to do. That's the process of doing this, right? So we wanted the cumulative, or the density for y. We did the substitution. To get back to our focus on x, because we started with x, and we had to deal with the square issue, and then there's not a unique solution. And then split this into 2 pieces, 2 cumulatives, take the derivatives, and then work through the details. But it ended up being that's the density, that's the answer. So we start to get some idea that there's ways that once you have the random variable, and you're going to, we do have some time. Right, let's see. Right. I've been kind of maybe going fast. Thinking about finishing a little bit earlier, right? But anyway, are there any questions about those methods? Where we're going as you're looking through through things. In the book, 7.2 looks at thinking discrete random variables and a couple ways of figuring out distribution. Using CDFs to get the CDF of a new variable y from the CDF of the previous variable x is really 7.4 does the thing for going directly to the PDFs, right? Taking the density with the transformation, the inverse transformation, and then that derivative to make it work out. Right? 7.6 has things on moment generating functions. We might review that just a little bit. On as we go forward. There's another method in here called conditioning. It's a little trickier to get good examples to do, right? But what we're going to, we'll look at a few more examples, but then this 7.7 has things to do with 2 dimensions. And continuous. And so we'll do a little bit more. We'll probably do a little example of conditioning, but another problem or two to practice some of those transformations, and then start looking at the 2-dimensional things. And the homework would cover this part of it. There's also something on order statistics. I'm not sure if we'll do that on Thursday, but we'll hold off to doing that just a bit later. So, good. I was in some of my classes in that are an hour and 15 minutes. This is a little bit longer. So I went a little bit faster, so sorry if there were more questions, but we'll stop there. And then,
So with Thursday's work for you, Tuesday, second week of class, more things.
yeah.
So I wasn't sure before there was.
Yeah. Yeah, right. And so this would be the last one to do.
Right.
Here you go. Yep. And so when you take the, yeah.
Yeah.
You're good.
Perfect. Yeah, and then I'll be back for the final set.
Okay.
Perfect. Thank you.
Yeah.
Have a good night.
See you. Yep. See you.
Alice, I think it was Alice will take these ball.
Yep.
When we're talking about like taking inverse these functions, we talked a little bit about like being careful with like one-to-one-ness or something.
Right.
One-to-one. Do we also have to consider like onto-ness as well when we're doing these?
I mean, probably in an abstract mathematical sense, you would want to see that it matched up to the range of support with the variable. You could have something where it was chopped off, but most of the functions I think we would deal with in statistics would map a whole range to a whole other range and not have that restriction.
I guess I was thinking about it in terms of the y equals x squared example, because that's mapping exclusively to the positive, right? So I didn't know if it played a role, but
Right, so below 0, the cumulative density just has to be 0. So there's nothing, there's no negative values. And so at every positive value of y would map into 2x values. And so you'd have to be formally correct, you'd probably specify that the density is 0 before 0, and then it's that other thing after 0. Yeah. So, yeah, graduate course might really want to.
Oh.
To do that, to do it. It's why you mentioned the ranges, because, you know, it's, you do want to think about what range of variables you're going to have for things, but, right, so.
We just happened to be talking about that in groups, which is
Oh.
why I was, when you brought
Yeah.
up one-to-one, I was like, whoa.
Well, yeah.
It all
So,
fits
you know,
together.
with that discrete one, if you have these two things that add together, and your variable is bigger than is possible for the first one, you can't set the first one at 0. So the ranges of some of those summations for the discrete runs. And there's some, you know, hypergeometric distributions. That's the kind of the tagging, capture, recapture
Oh, okay.
ones, right? So if you have a population and some are tagged and some are not, what's the, you know, you only can ask about probabilities of certain outcomes, because you can't have more than the maximum or tag you tagged in the second sample. So there's some restrictions on the space there. So that would be, yeah, important in a formalistic sense. But by and large, our examples won't have that complication.
Okay.
So
Good to know. I can only be concerned about that with Professor Simons.
Yeah.
Have a good day, Professor.
Yeah.